Okay, so I'd like to talk about a few complexity results about the problem motivated by categorical linguistics. There are categories involved. I use quantum logic, so I hope people will be interested in quantum relations as well. So, why are linguists using categories? Mainly because it provides a convenient syntax and interface. So, we have a syntactic category, a semantic category. Both of them are strictly monoidal categories. And you have a functor between the two, which is monoidal, which translates the objects that you manipulate in your semantics to some category with concrete mathematical objects like modules or vector space and morphism between them. So, what does grammatical induction look like in this framework? Imagine you're a child and you learn the language of your parents. So what you have is just sentences. So a sentence is a sequence of words, so it's something monoidal. And you also know the meaning of these words because you observe them in context. You have some functor from this monoidal category and your semantic category. And you observe only a finite number of sentences because you can't just observe the whole language. And your task is given this functor, just factorize it by f, so that you can actually so that, yeah, you can find factorization of this morphism by f. And the crucial condition is that the sentences you observe are grammatical. So what it means for a sentence to be grammatical? Well, it means that the object is linked to the units of your monoidal category. That's the framework in which we are working. So you have this finite set P, and you want to lift it syntactic category such that it's grammatical. So let's have a look at a quick example. In the case where your semantic category is in fact closed and your syntax is pivotal. So the difference between the two is that you have the symmetry in the semantics that is in the syntax. So we can imagine that you observe a sentence with 4 words, x1 to x4, and that we know that the meaning of all these words is there's particular types below, and there's types into reduced units by some induction. Withdrawal of an object to cancel the object. As you have symmetries, we can have crossing and rejection. And your task as a child is to lift it in the semantics. It doesn't like, excuse me. So concretely it means that you have to remove the crossings because you don't have symmetries in the things syntactic. So one way to do it is to permute as types, but you can also do it another way, of course. And then you observe another sentence, like this one. And now your task is again to lift this to your syntactic category. But you have to do it in a consistent way. So the pre-image of x1 has to be the same for the 2 sentences. So this rules out the second solution. So, well, this example is not linguistic. It is just to show you the combinatorial we have this problem. And in this particular example, we can see that in any solution, the type of this A will occur before the C and B. And with this kind of ID, you can actually reduce an NP-complete problem with this grammatical induction. So it's a between-S problem. Given a finite set A, some family of triples of A, you have to find the total order of A such that for each triple, you have one of these inequalities. And it happens that this problem is in So we can, for any instance of this problem, we can translate it to some artificial grammar induction problem, and hence it shows that this particular instance of grammar induction is incomplete. So if you wanted to make an analogy with quantum computing, you could say I am a quantum computer scientist, I develop a new quantum algorithm, and I want to draw diagrams of my algorithm in a paper I have to write. And I want to find a consistent way to order the inputs and outputs of my gates among all my paper. This is drawing speculation. So if you look at the bigger picture, we don't have only pivotal and compactors categories, we can also have a look at other categories. So at the top, you have this compactors categories where you have two quotients, right and left quotient. This corresponds to the Lambda equivalence. If you have a symmetry to this category, you have a symmetry closed category, which would correspond to the times for the lambda factors of pairs, for instance. If we choose instead to replace these quotients by adjoints, you get a continuous category, which corresponds to three groups. If you add that this left and right adjoints are actually isomorphic, you get the pivot category here. Then if you add symmetry to these two categories, and if an object and its dual are isomorphic, it will start drawing this category. And you can also choose to swap the symmetry of duality to this figure. So all of these arrows, which are functors, are an instance of the problem. So we can try to lift objects in any of this category to which is upper in the hierarchy. And so what we show is that these two instances are complete because we reduce the betweenness problem to them. Basically, it works the same way for subgroup case because we forget the symmetry. We can also show that these two instances are incomplete by reducing the satisfying component of this primary induction problem. And one thing we can do after that is to compose the two results. So given the complexity of two functors, what is the complexity of the composition of the two functors? And it happens that in some cases, when some conditions are met, you can actually show that this is also incomplete. And I'd like to extend these results to the yard. And why is it interesting? This categorical view is new, but some algorithms are already being devised by some people. So it would be nice to characterize the complexity of these two algorithms. So you can see I'm almost there. I just need to do the pivotal to autonomous case. Because the complexity of these two algorithms is unknown for now. So that's it. Thank you.
Questions? Okay, you mentioned two works on the previous slide. So those people, are they linguists or category theorists?
Yes, they are linguists. They divide algorithms without having category theory in mind. But what they say is that they are trying to induce a proof of grammar based on some times, and they had no idea that this was a subgroup at first category, but actually exactly.
Could you maybe say again about the advantage of a categorical approach in this domain?
Well, the advantage is that it's very convenient talk about type systems in general, because you have objects that play the role of types, arrows that play the role of reductions, because it's also used a lot to actually give semantics, distributional semantics, and integrated semantics. So various kinds of semantics of natural language inspired by this category. So it's not only a syntactic and combinatorial approach, attention, it's also used for semantics.
I see. Anything else? Well, some?
Can I check out that the 2 and 3 are not sure what the complexity is? Or?
So yeah, they gave the algorithms without actually analyzing the complexity of what they did. Because it's quite hard actually.
Josh?
When you define a string of words to be grammatical,
Yeah.
it says that there is a reduction to the unit of the category.
Yeah, so it reduces the unit. But actually you can choose to reduce to some other object. If you define some object to be the type of a sentence, you can say that the grammatical objects are objects linked to this particular object. The results here are not dependent from this particular assumption.
Okay, let's thank the speaker again.